slow. Yeah. Okay. Good. Yes. Yeah.
The record is on, everything is on.
Okay. It's good to go.
Can you try and refocus the camera real quick? There we go. Thank you.
Is that better?
Yes, sir. It did it on its own, I think.
Okay. Okay, well, today I'll just review the stuff we've been doing on the convergence of finite element stresses. Then I'll go through problem set 3. I also have a comment on problem set 2. And then I'll give you some information about test 1, which is on this coming Friday morning. And in the end, I'll take questions about test 1. Before I start, I did get a question in a box. Can the examples that I did in class be found in the book? The answer is typically no. Okay. There might occasionally be an example I did that came from the book, but typically no. There are relatively few sample problems in the book. I think in this whole chapter 4, I think there are about 3 in this version of the book. Anyway, let me recap how you do the check finite element stresses for convergence. This assumes that you've got a working code that's already been verified, which for all the standard codes is a very reasonable assumption for these sort of elements. There are some tricky elements where that's not necessarily true for major codes like ANSYS and Abacus, but for these sort of code, these basic elements, which are the ones that are, these and their 3D counterparts are the ones that are most used in practice. These elements have been fully verified. Then there's this business of your interaction with the computer. And last lecture, I gave you a reference to a book by Moavini, which does a lot of examples where they lay out step by step what your input for ANSYS is. And so there are some courses. ANSYS offers some courses. There's a course here, a technical elective, where you can get this sort of training. But if you can't get that, that book's about as good as any for teaching yourself. So assuming you've made the correct instructions to the computer, then we're going to check and see if these stresses have converged. And this is the sort of thing that could be tested on test 1. But you don't have to get stresses, of course. You'd be given stresses and then asked to check them for convergence. And the way we check for convergence in this course, there are occasional other ways, but this is one of the most robust ways out in practice. is we take element extents and we halve them. Now, the element extent size of the elements varies throughout the mesh, but if it's 1 in one place and 4 in another place, then it goes to half in the first place and 2 in the second place. So you do this for the average element size. Okay. What will happen then is the number of elements will quadruple in 2D, and that's what the focus is here. Okay. Once you've done that, you're going to have results, and you need results from 3 meshes, and then you can check for your convergence requirements. I think somebody needs to put their computer on mute. But so, as far as this course is concerned, let's see. This decision of which stress of interest, you do not have to make it, okay? But you'll be told it's at some maximum stress at some location. In practice, you have to make a decision. Sometimes in a configuration, there are multiple stresses. You check their convergence for each one at its location by itself. Okay? And you have to keep the same stress component there. There might be more than one that's not 0. And you pick the one that's of interest. And of interest means potential to cause failure, because this is what you're designing against. Then as you refine the mesh, you'll get a stress increment, and that's what this delta sigma m is. It's the increase in the stress of interest from mesh m-1 to m. M is the mesh index. Then for it to meet the converging requirements, these increments have to be the same sign. They could both be negative or both be positive. And either way, their product will be positive. Okay? They've got to be moving in the same direction, and they have to be of decreasing magnitude. Okay? If that happens, then we can estimate the stress, the error, as I showed you before, as follows. Now, you can only estimate these errors once these converging requirements are met. If these are not met, it's possible that the analysis is diverging. It's also possible it's not yet close to converged. Okay? Either way, you can't estimate the errors. Once this starts to happen, then you can use this formula. And what will happen here, these two will be the same sign, and this is bigger than this, so this is greater than 1. Okay, it may not be much greater than 1, but it's going to increase the error from its change over its position right now. We're just interested in absolute values of this. Okay. Once you have this, we can classify the error levels as follows. We put a hat on this just to denote that it's an estimate. If we remove the hat, it's the actual error, and it doesn't have this formula. And the actual error happens in test problems when you know the answer. And we've done a few of these, and so there are some epsilon m percentages that are not estimates. But in practice, this is what you'll be doing. Relatively seldom will you have test problems, but you will have some. If this estimate, so what you're going to establish your error level with typically is going to be with estimates. Okay. If you did have the true errors, you could use that, of course. But for the most part, you're going to be estimate. So if it's less than 5%, that's satisfactory. If it's less than 1%, we're going to call that good. Obviously, it's also satisfactory. Right. And we keep going down by a factor of 5. So less than 1/5 of a percent, or 0.2, is excellent. When you get out and practice, you're going to find that people have their own error levels. They won't be markedly different from this, but they could be different. I told you that Pratt & Whitney takes 2.6% or something as good. Well, that's sort of between these two. I'm not quite sure what GE does. Okay. What this implies with this is a system you need to use in this course. Okay, so there's no debate for you what these levels are as far as this course is concerned. I'm just telling you in practice, like you could get different ones. But there's an implication here then, is that if you're greater than 5, that's unsatisfactory. And what this would mean if you got an estimate like this is that you need a further mesh to try and get the errors, or you might need more than one, but at least one further mesh to try and get the errors to be at least satisfactory. Okay. Which of these levels you pick for a given application is going to depend upon how far along you are with the design and how important the design is. There are some crude designs. Some of the stuff I've seen in the oil and gas industry is seriously over-designed, and that's because that makes it safer, and the costs of being over-designed are insignificant. When you have moving equipment like automobiles and jet engine and plane, when you add extra weight, then you're going to add extra cost to the operating. The extra cost of putting some extra steel in a pipeline is not that big a deal. There's a question here, for an error estimate in an exam, do we calculate all the intervals? Well, you have to calculate enough intervals to decide this. So to make this decision, you're going to have 3 intervals. Sorry, you're going to have two stress increments, okay? You can't make this decision unless you've got 2 stress increments. And you need a minimum of 3 meshes to get 2 stress increments. So after you have 3 meshes, but you'll see this a little bit when I go through problem set 3, after you have 3 meshes, you can get 2 increments, you can check this, and for the 3rd mesh, you can get this error, okay?
Where can we find practice problems for pressure vessels?
Sorry?
Where can we find practice problems for pressure vessels?
What for pressure vessels? I'm sorry.
practice problems. Where can we find that?
I don't really know. Nothing quickly comes to mind. Okay. The formulas for pressure vessels are fairly simple, the ones that you've been given. And there's a couple of these in problem set, the beginning of problem set 3, which I'll be going through. Okay. And so after you go through that, I think you should be okay with the pressure vessel.
Okay, thank you.
But nothing quickly comes to mind. A number of the books don't have that Shigley formula. The formula for the hoop stress is P R bar, the mean radius, divided by T. And for the longitudinal stress, it's P R divided by 2T. And a lot of the books don't have R bar, which is just lazy on the part of the authors writing them. Shigley introduced that, which is an improved estimate, about 1950, I think. So I think they copy from each other or something. But anyway, so I don't know good mechanics and materials books that do this that well. One last little thing here, you can also estimate the convergence rate. This is the key thing you're going to want to practice is these errors, but sometimes you want to estimate the convergence rate, and that you do as follows. So with star has that these two are the same sign, so the quotient will be positive. They're both negative. Negative divided by a negative is a positive, and of course, when they're both positive, it's a positive. The log of a negative number is an imaginary number. And so with star, this is real. And positive. The log of a number that's bigger than 1 is positive. The number less than 1 is negative. But this is bigger than this, so it's going to be positive. So you really can't do this unless you've got star as well. Okay. Why this is of some interest if you have 4-node quadrilaterals, which is what the 4Q stands for, then this convergence rate tends towards 1. That's because the missing thing in the elements is linear. The first polynomial missing from a power series expansion for the stresses is the linear term, and so that would tend to converge linearly as you refine the mesh with this 2, yeah, with a mesh refinement factor of 2, which we've had at the beginning. On the other hand, for the 8-node quadrilaterals, you can get both constant values for the stresses and linear values. So the thing that's missing there is the quadratic term. Now, this is generally true. Sometimes these stresses don't have a power series, so you shouldn't count on this being true, but more often than not they do. And so you can sort of see this. And if this is not happening, that should raise some questions. And so calculating this is not an unreasonable thing to ask you to do. We can combine this with our area estimate as follows. If you take this over the other side, you get log 2 cm hat times log 2. That's the same as log of 2 to the cm hat equals log of this. You remove the logs, and this thing here tells you that 2 to the cm hat is the same as the quotient of the stress increments. This is what we had in our bottom of our area estimate, so we can put this in here. So the area estimate It's easier to calculate error method using this. So I encourage you to use this. But here's another form for it, and it has some implications. The numerator stays the same. But now we'll switch this.
Could you move the paper down, please?
Oh, yeah, sure. Sorry. Okay. And what this tells you, look, if CM hat was to tend towards 0, you had very small, low convergence. Two to the 0 is 1. 1 minus 1 is 0, so this goes to infinity. So the reason for showing you is this, there's a penalty when you get slow convergence rate. You get very large errors. And what that'll tell you is you need a lot more meshes to get the right result. Okay? That's the only reason for showing you this. Now, I'm going to start going through the homework, but there are any questions about the stuff I've just recapped on finite element stresses, how you check for convergence, and how you get error estimates. So are there any questions from anybody?
On the test, if you were to ask us for the error estimate, do we have to do the convergence rate?
What does this say? Oh, I'm sorry, I misunderstood your question. No, I misunderstood you. No, I misunderstood your question. Totally reasonable. No, if you're asked for an error estimate, you don't have to get this. Okay, this is ancillary. Okay, so
okay,
that's a very reasonable question. I misunderstood.
Yeah, I also had a question just about
formatting. Let me respond. So if you're asked to get errors, then what you have to do, what I was pointing out, you have to do, so the first thing you have to do is check this. Okay, so you have to check these convergent requirements, not rate convergent requirements. Right. Okay, and so you can't do it until you've got this. Okay,
sounds good.
Okay? Once you've got that, then you can calculate this. This is easier to calculate than this. Okay, this requires you to get the error estimate of the convergence rate, and so this is an ancillary thing. It's conceivable you could be asked to do this as well. We've just asked to get errors, then just get this. Okay, that answer
sounds good. Yes, sir. Thank you.
Yeah. And in practice, that's what most people do. Okay, they don't bother with it. But you know, if I'm working on something, we've done quite an extensive piece of finite element. I quite often, it doesn't take long to calculate this, and it's a reasonably lengthy job. We spent about a week doing it. Then I quite often get this and see that it's behaving like it should for the right elements, whatever elements we're using. But it's an ancillary thing. And so just ask to get errors, just do this. Any other questions?
Yeah, I had a question just about how we should format our answers on the test for a question like this.
Okay, we'll get questions on the test at the end, okay?
No. This is about checking the convergence rate.
Oh, I'm sorry. Okay.
Yeah, I know in the past you've just looked at the numbers that you calculated and said, you know, you can see clearly from the numbers that it's decreasing and that they're both positive or both negative. Is that enough to do on the test, or should we actually write everything down?
No. So okay, that's a very fair question. Yeah. So you've calculated these stress points, and you could just say convergence requirements met for mesh, and give which meshes they're met for. Okay. You don't have to write down. You don't have to write this out. If you can see it, just looking at it, you can say convergence requirements are satisfied for M equals, and give what meshes you're talking about. It may not be all the meshes. Okay. So you can just look at them.
Perfect. Thank you.
Okay. But you don't have to write this down explicitly. Okay. Any other questions? Okay, well, let me go through the problem sets. And first off, I made an error in the solutions for problem set 2 for number 5, which Ben Champlain pointed out to me. I'm very grateful to him for. Here's the problem. And I did something really silly, and I don't want you to do it, okay? But here's a corrected, I'll post these solutions. You don't need to write any notes. I'll post these solutions this afternoon. To get the bending moment at the first one of these sprockets, or they could be pulleys, okay, the bending moment is not the load. I had it the load times the distance. It's the reaction, RA, times the distance. So you have to get the reaction, and this reduces my values I had by 25%. The rest of the problem is okay. You've got a horizontal plane and a vertical plane. You have to get the reactions in both, and they're a little different. And I worked in from this end here, this one, but you could work it from this end and you get the same answer. So I have no idea why I skipped this important step. You need a free body diagram to get these reactions, to get your bending moment diagram. It was just a really stupid thing for me to do. But this will be posted. So it's a good thing I'm not taking this course for credit. So the corrected solution is posted. Here are some pressure vessel problems. The first of these is just a piece of algebra, but it's instructive because this is basically all you've got for pressure vessels, what you have in this class. The PI is the internal pressure, then it pushes out, it's like blowing up a balloon, and it stretches things. For cylindrical pressure vessel, you get about twice the stress in the hoop direction as in the longitudinal direction. And these are the two formulas which I mentioned briefly. This is the Shigley formula, PI R bar over T, and this is the longitudinal stress, the internal pressure times R over 2T. R bar is the mean radius, so it's R plus T upon 2. Now, to do the external pressure by itself, I gave you this rule. Here it is. You just add the pressure and change the sign. So you just add, this is going to become P naught, and you add P naught. So it's P naught R bar over T plus P naught, then change the sign. That's all there is to it. The same thing for the longitudinal stress. Obviously, this changes to P outer. Okay? Now, when you're pushing in on things from the outside, it goes into more compression. But it goes into more compression than just minus sign does this. You have to add P naught, then multiply through by -1 everywhere. Then the last part of the problem, you just put these together. There's nothing to that. As I said, these things will all be posted this afternoon. This next one was a pressure vessel, and you had to do some calculations here. Okay? Well, here are the calculations. The pressure was 800 kilopascals. I did everything in megapascals, so that 800 kilopascals became 0.8 megapascals. Megapascals are the most common unit for stresses in engineering, the METI. Okay. Then R bar, R in this thing here was 1.8 meters. The thickness was 20 millimeters or 0.02 meters. Okay, half of that is 0.01, so that's where the 1.81 comes from. There's no mistake there. And this is divided by 0.2. That gets you a hoop stress of 32.4 megapascals. You apply this formula, and you get a longitudinal stress of 36, about half. Okay. In this case, the thickness is pretty small, so Shigley's formula doesn't make up much difference. That's not always true in practice. Now, it asks you to get the maximum in-plane and out-of-plane shear stress. In-plane, the maximum will be half the difference between sigma H and sigma L. Okay. But out-of-plane, it's the difference between the biggest difference between the principal stresses. Your biggest tensile principal stress is sigma H. The biggest negative or compressive principal stress is the applied pressure. And so if you have sigma H minus P, you get sigma H plus P and divide by 2, and you get a significantly bigger out-of-plane shear stress, about a factor of 2. And this is common in cylindrical pressure vessels. Then it asks, now, oftentimes in the book, you're asked some of the book problems, these sample problems, try and get the angle where the principal stresses at. Typically, you don't care about this. In this particular problem, you do care. You're going to have a weld, 55 degrees here. This weld will have a certain efficiency where it's well done in the oil gas industry, probably about 80%. That means it breaks at 20% less than the parent material you're welding together. That weld will separate. And so this becomes a critical thing to look at and in particular what the normal stress is here. And so to do that, then you have to use this combination formula. Now, I'm going to give you these formulas in just a second, but in fact, let me do it now. It's not clear to me how much you had of this with Dr. Wahab. So just to be on the safe side, let me give you the formula for stresses on an inclined plane. This is called Moore's circle, but you don't need, you just need the formula. I'm going to call this angle phi, but you can call it something else. I think you probably had this, but just be on the safe side, I'm going to give it to you. So what you do is you do equilibrium little triangle, and when you get through that, doing that, then you find what sigma phi is in terms of the stress components in XY coordinates. And the shear stress in XY coordinates will all be converted to normal stress when you get to a principal stress. So tau phi would be 0 there. But this is for any general plane. So tau phi is not in general 0. If you make it 0, you get principal stresses. So half sigma y minus sigma x. That's not an error on my part. It's the opposite sign to that. And those are basically the underlying equations for Moore's circle. But in practice, you use them like we use them on this problem here. You occasionally want some stress on an inclined plane because you have a weld there or some other reason. You might have a small groove there or something like that, and you want to get the stress across it. In which case, this part's going to be posted. Then this angle is 55 degrees. So this is 35. So phi is 35. It's not 55. This is the angle of the weld is 55 degrees. This phi is inclined with respect to the x-axis. Okay. And so you take the 90 degrees here. This is 35, 35. So phi is 35. Okay. If you like, 30. This is 35 here. There is no shear stress. This is a hoop. This is a pressure vessel. So this tau xy term is 0. And so these two terms are the first two here. Okay. And this is the first term here. And then you can calculate it as it's done. Okay. And you find out what, in particular, what you'd be interested in is what's the stress across the weld. Okay. There's some stress concentration problems. As I said, all this stuff is posted. Here's a stress concentration problem. This is a matter of looking these things up in the charts given in the book. And if you had something like this on a test, you'd be given that chart. And so here's one of these charts. There is a little bit of an interaction here, possible interaction here between this notch, almost invisible there, but there's the two notches. They're about 3 plus center to center diameters apart. There'd be very little interaction. But whatever interaction there is would increase the stress concentration. So it's a little non-conservative. Here's the plate with the hole. Okay. Down here. And you have to go get D upon B. Well, these charts have their own notation. They're not even consistent from one chart to another. So you have to read on here what D is and what B is and what H is. Okay. Although these results are independent of H, basically. Well, the nominal stress is not. Okay. And so that's done in the work solutions. There's another chart here. This one here is pretty easy. D upon B is 0.15. And you go up here and you get KT. Okay.
We actually had a couple of questions on this problem when MD was going over the homework on Friday, and we wanted to see what was going on.
Okay.
When you're calculating little h.
Calculating which?
So when you're calculating, for instance, little h for the notches, because you have to calculate h over h.
Yes.
Why do you exclude the whole? Why do you calculate it as 170 and not as 170 minus 30? Because the whole isn't there.
I didn't. Okay.
When you say for notch, you have h over h as 200 over 170. Why isn't it 200 over 140? Wouldn't the whole be excluded since that material's missing?
Not okay. It's what you're saying is not unreasonable. Okay. I think in the answer, I assume there's no interaction. If there's no interaction, then you don't bother taking that whole off. What you're starting to do, in fact, this is like one of the later problems. What you're starting to do now is try to get a better estimate and try to be a bit more conservative. That's not an unreasonable thing to do. Okay. I thought the separation 3.3 diameters, there's very little, 1 or 2% interaction at about that. And so because it's very low, then I took H was, let's see, where's the problem? So it's 15, 30, yes. So we didn't exclude the whole, okay? We just took the total thing. If they started to get closer, one way you could attempt to track interaction between the two stress concentrations would be to do what you're saying, okay? Okay, so once you make this assumption, then you just ignore the whole. Okay. But if you start to be worried about this, let's suppose it gets down to about 2 diameters, then doing what you're saying is a reasonable thing to do. Okay.
So I had thought in previous classes we'd said the threshold was once it was 4 diameters, you can ignore it.
That was about 0.1%. But if you go look at that that stress, it's pretty low at 3 diameters or 3.3 diameters.
Is there a general rule that we should be using for this class to when we're allowed to ignore it?
I'd say anything more than 3 diameters, don't worry about it. Okay.
Okay, perfect.
Okay. Yeah. I mean, you could go look. Why am I picking that? I can't do it in my head, but I think it's certainly less than a 5% effect. Okay. And so it's satisfactory. So I think it's more like 1 or 2. And so say to give you a definitive rule, 3 diameters, you don't worry about interaction, center to center. Okay. But you could start doing what you were saying when it got closer than that. It would be a way of trying to allow for interaction. It's not precise, and there are some solutions when you have 2 stress concentrators, and you could go look in practice. Obviously, you wouldn't do this in the test, but in practice, you can go look at Peterson stress concentration factors and see the sort of interactions. There are 2-hole problems and stuff like that, and you can see how much it does, and you can get a factor from that, okay, which would be a better way of doing it. But if you didn't have access to that, then you could do something along the lines of what you're saying. The solution for the next one here is given. This is the book solution. I've checked it. I think the numbers are correct. One thing I would point out here, to do a Benny moment diagram, you don't need to do the shear force diagram. You know that dm dx equals v, so some sort of check, And if it helps you, I guess that's okay. But I don't think you're going to have time to do that sort of thing in a test. And most mechanical engineers don't bother with this. Civil engineers tend to worry about shear forces much more. Very, very occasionally in stubby beams, the shear force produces a significant shear stress. It is really rare. It is really rare. Okay. So otherwise the solution is just fine. But here's something that's a little bit like what you were just asking me about. This is an ellipse, or you're going to approximate this ellipse. And here's how I did it, which is along the same sort of lines of what you were talking about. I'll come back and do this in a minute. So what I did was I put an ellipse inside this. That would mean A would be 3 inches. And this distance here, this is 2 inches across here, 1 inch plus 1 inch. And so B is 1 inch. So the stress concentration is 1 plus 2 times 3 over 1 is 7. But I multiplied it by the average stress in here, which I divided it by the average stress in there. And so I had an integral factor of 2 upon 5, which increased the stress concentration factor by 5 upon 2. In other words, I said because the stress is going to be bigger, then I'm going to apply that stress to the stress concentration factor. And so sort of doing the same sort of thing you just asked me about, you get a rough estimate of 18. Whereas if I hadn't done that, if I just put this as sigma naught, which would be the answer for an infinite plate, okay, then I would just get 7. Okay. So there's a little bit of judgment doing stuff like that.
Where did you get the sigma naught from?
Sigma naught is the applied stress out here.
Okay, so what value is that?
So I said the value here is 2.5 times as big, the average value. But this is 3, okay? So this is 2. Okay? So the average stress here time, so let's call it sigma average. Let me write that down. Sigma naught times 5 is sigma norm, and this depth here, 3 from 5. So the nominal stress in here is 5 upon 2. I said the maximum stress is KT times sigma norm. And KT was just 1 plus 2 times 3 upon 1 times 5 upon 2 times sigma naught. And that gets you 17.5 or roughly 18 times sigma naught. Okay. And what I did was I put an ellipse inside this, like this. Okay.
Okay. So you didn't use a specified value for sigma naught.
That's right. You're just getting KT.
Okay. All right.
Cool. So you don't need the value of sigma naught. You're just getting what's the stress here? What's the stress here relative to this? And that's the stress concentration factor. Okay.
So we couldn't use the formula 1 plus 2 square root of A over R?
You could, and you'd have to go get what R is. Okay. And R is B squared upon A. So you'd just be doing the extra calculation. You'll get the same answer.
Okay. Thank you.
Okay. It's when you're calculating elliptical stress concentration factors, if you're given A upon B, the easiest formula to use is 1 plus 2A upon B. If you're given the local root radius, okay, or you wanted to take this here, I think when you're doing this, you could, I can see what you're thinking. You could perhaps take the R here as being 1 inch.
Can you see what you're pointing to?
And you see which one's bigger. Okay, I'm pretty sure the one I did is bigger because it's got a smaller radius. I put it in ellipse. That's going to have a smaller radius than this radius here, and so that'll be a bigger KT. okay? So you want to try and be conservative, so you want to pick the bigger value. Okay, well, here's the answer to part B, and this goes to, so I'm writing out the solution here. You take, you get the increments, and they're continuously the same sign and decreasing. And so I wrote this all out in the word solution. You could, to answer your question earlier, you could say convergence requirements, check, m equals 3 and 4. So they check. Sometimes it'll just be for m equals 3, and sometimes it might be just for m equals 4. I'll explain that in a little bit. Then once you've got these convergence requirements, you go calculate the error. It's 0.29 times 100 divided by its value, 21.491, times delta sigma m minus 1, 0.522 over 0.29 minus 1. And when you calculate that, you get now 1.7%. Now, as I think I tried to explain earlier, you want these numbers to 4 and 5 figures. So when you take the differences, ideally you'd like at least 3 figures and certainly 2. Okay. So that's why you have these stresses of so many figures. But once you start to get your error estimate, and for that matter, convergence rate, you really only give it to 2 figures. That's all it's good to. And you never give the third decimal place. Okay. So if this turned out to be 0.063, you just say 0.06. So because they're both estimates. This is almost halving, and these were, I believe, 4-node quads. It didn't say, but these were probably 4-node quads. Now, some comments I wanted to make on these here. These are set, they tell you what elements been used. These are 4-node, and this is 8-node. And then they ask you to get estimate the error whenever possible, okay? And then you can compare it, because these two are actually test problems and we have an answer. And here's what happens when you do this. Here's the first one, okay? The exact answer for this was 90.25. Very seldom do you know the exact answer, but here you do. So you can see this is headed in the right direction. It starts off with a huge error. It's not even halfway there. This is a very coarse mesh. But now it's getting up there, okay? And what happens initially, because the convergence rate, because you're taking these big steps, okay, as a final element trying to move towards 90, it keeps taking big steps. So these steps are comparable magnitude, so have very slow convergence rate. So you get very large error estimates. That's not of no consequence. The actual true error is 25%, so it's not satisfactory anyway. Okay. So the fact that this is much bigger than this does not matter. Neither one is acceptable. Then down here, they're still much bigger. This is more than a factor of 2, but neither one of these is acceptable. Okay. And these are both above 5%, but now it's getting close. Okay. And so if you kept going, then these error estimates would start to tell you you're okay, and in fact, it would be okay. And if I jump ahead to problem 3, to the third step, then these start off better. The other one started at 38, but they move more quickly towards the right answer. And so these things start going down more rapidly, and you get 100% there when the true error is 15%. Again, gross overestimate, but of no consequence because they're both unsatisfactory. This one here is close to satisfactory, and your estimate saying it's quite unsatisfactory, but they're still both satisfactory. And here you've closed in, and that's what happens with these error estimates. When they start off with crude meshes, the error estimates themselves are crude, okay, but they overestimate. And so it's not a problem. Okay? And so in terms of the levels, this would be unsatisfactory, unsatisfactory, and good, but so would this, unsatisfactory, unsatisfactory, and good. Okay? Here's the comment on the sigma m above, all pass, hard to read. The convergence requirements, and they're calculated with this. Okay. Now, a curious thing happens for this middle one. These delta sigma m do pass the converging requirements. They're all the same sign and they are decreasing. They're decreasing very slowly. Okay? And as a result, because these are close, that quotient gets close to 1. You have delta sigma m minus 1 over delta sigma m minus 1. That quotient gets close to 1. 1 minus something that's a little bit bigger than 1. Sorry, other way around. Something that's a little bit bigger, 1 minus 1 is a small number, so you get very large, and your error increases.
Professor?
Sorry?
What number is on sigma m for m equals 3?
Okay, what this number is?
Yeah,
Well,
I think the problem statement that we were given was 14.633, not 83.
That could be. That could be. Just let me check. Yep, 14.33. Yes, thank you. Thank you very much. I'll correct that before I post it. It's not going to make a major difference to the results. I still shouldn't get it wrong, but yes, thank you. I'll correct that. Okay. Well, what's happening here is this problem, we deliberately did a problem that had a very weak stress singularity. And what happens with these weak stress singularities, you can't report a finite element value if you've got a stress singularity. You can't report a finite element value unless you're converging. Well, here you could report this and say it's converging according to our converging requirements, but the error is unacceptable. Okay, and so you wouldn't report it. And what's happening, and this happens at these stress singularities, is you have some regular stresses there present, and they are converging, and they're going down. And the weak singularity is diverging. That stresses are going up, but they're not going up enough to mask or to overcome the fact that you've got some converging stresses. And so the thing looks like it's converging. The error estimates I've given you, and this has been consistent for dozens of problems, will always be huge. And so it'll tell you, don't accept that stress. What happens eventually, if you keep refining this mesh, this thing will start to diverge. This thing will start to increase, okay, reflecting the stress singularity. But so what can happen here is you can get an error estimate on a singular problem using the estimate I've given you. Fine, but it'll always be unacceptable. Okay? At least in our experience, it'll always be unacceptable. And there's some underlying reason for that. And it's because the divergence of the singular part of the stress has not yet overwhelmed the regular part, but nonetheless, it's screwing it up and making the convergence rate extremely slow. The convergence rate here, let's see, let's take the convergence rate. It'll be this divided by this. This will be a little bit different when I correct it, but it won't change it too much. The convergence rate is 0.03, okay, so it's very nearly 0. And some of the stresses are converging. That's why it is, in fact, positive. But eventually that'll stop. Are there any questions on those problems? Or any of these last problems here on checking convergence for finite element stresses? Any further questions? Okay, let me make some comments about this. Here's the deal. I'll go through these comments now, and after that, if you've got questions, you can go ahead and ask me. Some of you have asked me questions as an individual basis. I understand why you do that. From this time on, you cannot do that, because if you ask me a question, so somebody sent me an email, and I respond to the question because I'm going to give the same answer to everybody in the class today. But from this point on, tomorrow during office hours, for example, you cannot ask me a question about the test, because I can't give you the answer and not give it to everybody. Okay? But I think pretty much all the questions we can handle today. So think of any questions you have. By all means, ask me those questions today. I told you what the test was on. Basically, it's on the the problems that we've done, which would be examples, I think 1 through 13 minus example 4, and problem sets 1 through 3. There's a couple of sample problems, and not even all of those sample problems. One of them asks you to draw more circle. We haven't been doing that. You'll be given material properties.
Can you refocus the screen?
Sure. Let's see.
What if you put a pencil down right on the top edge of your paper? It might focus on that pencil and then it would focus.
Oh, okay. That was a good idea. All right. So if you're going to look up a KT, you'll be given the chart to do it, okay?
Dr. Sinclair.
Yep.
The KT charts are the ones like the ones in the book where it has
That's
the
right.
picture of the picture of the figure.
Yes, and these charts are all self-contained. You know, they define, admittedly they change notation from one chart to another, but they're going to define their geometry on the chart, okay? It's conceivable I could give you a chart from Peterson instead, but it'd be the same thing. It'd be a very similar chart. Actually, the charts from Peterson are a little bit easier to read. But again, it would have a figure showing what the configuration was and what the geometry was. And so you can figure out, given the problem, you can go figure out what you need to enter the chart and get it. Okay? In practice, I usually use a scale to read these charts. In a test, you can pretty much eyeball it, okay? But I usually use a scale, typically in 16ths or something like that, or millimeters, to try when the value ends up being between some given values to try and estimate it. But in a test, you can eyeball. We're only looking for getting it reasonably correct, plus or minus 0.1, I would say. The units you use will be pounds force for US units. And as I've told you, you're going to experience both. So there'll be SI problems too, and they'll have newtons. Feet and inches. Meters and millimeters. But the key one is stress. And for US units, you have either PSI or KSI. Either's okay. Typically, for SI units, you have megapascal. Strictly speaking, in SI units, you're not supposed to have a number that's bigger than 1,000. So 1,100 kilopascals is actually 1.1 megapascal. I'm not going to police that on the test, but the following, I've seen this. That's not a unit, that's a pascal, okay? So don't use that, you'll lose a quarter of a point if you use that.
Dr. Sinclair.
Yep.
For PSI, can we put pound per square, like LB over inch squared?
No, just write PSI.
Okay.
Okay. If you did this, that's not incorrect, okay? But this is the normal way people communicate answers, okay? PSI and KSI. And the SI has far stricter rules, Okay, so this is said to be not a unit in SI. Okay? They actually explicitly say that. Okay, they're far stricter. They come along a lot later and they laid out punchables, and they had that rule of not more than 1,000 too for lengths and stuff like that. I'm not policing that, but if you get work somewhere where they use SI, you'll need to police that and use prefixes. You can join the meeting sometime but after 8 on Zoom, and the test will become available about 8:30. You'll have an hour and a half to do it. If you join late, you'll have less time.
What did you say about the Zoom?
You can join the Zoom meeting at about 8. I'll never put that. Might be a little bit after 8. It'll start. Okay. You could download or on your tablet. I'm not quite sure how to spell that. If you're comfortable just working directly on the computer, that's fine. Okay. You can download it. There's space to answer questions in the test that's given. Okay. That'll take you a few minutes. So rather than do that, I would suggest you just work on paper, and then you can scan it at the end. We'll give you some time to scan it at the end and send it to us. If you do that, if you're more comfortable answering on paper than actually answering on the computer, then be sure you've seen your stuff in order and you clearly indicate which questions you're answering. Okay? Be clear about that.
Are we able to print it out?
Sorry?
Are we able to print it out and then write on it?
Yes. That's the first option. Okay.
Okay.
Okay. Or you can just put it on paper and just say this is 1A, 1B, 1C, and stuff like that. Okay. Or you can do it straight on the computer. Okay. And then you'll have to scan it and put it back. If you give me 2 answers, we grade the worst one. So don't give me 2 answers. Okay.
Can we take it on like an iPad or something like that, a tablet, or does it need to be written, the answers written on the paper?
You as long as you can get your answers to us, then that's okay.
Perfect. Thank you.
If you can't get your answers to us, then that's not okay. All right.
Also, what did you say about our camera setup? What are the requirements on that?
Okay, just a second. I haven't finished everything. If you get extended time, I've only got 1 student who sent me the letter for extended time. So I need your authorization. Okay. The fact that you've given it to somebody else, it's not me. Okay. So you better get that to me this morning. What we'll do is we'll try and separate the people who get extra time and put them in 1 Zoom meeting. And if we can't do that, and they're mixed in to the extent that they'll be just getting extra time in the Zoom meeting, to the extent that there's a little bit of disruption towards the end of the regular time, the people who get extra time can stop work, they can think about the work, but that time will not count against their extended time. With a couple more comments, then I'll take any questions you've got. I will send you an email with how to set yourself up so that we can essentially see your workspace. this will be essentially the same approach as if you've had Dr. Gontier. Okay. I will post solutions on Thursday afternoon. Okay. As I think I mentioned to you, I found from past experience that putting these up too early, people go look at them instead of working them, and then they think they're easy, and then the same sort of questions on tests they can't do. I'll have office hours tomorrow. You can email me. I may be able to respond to your question via email. If you include a phone number, I'll call you. The last thing I'll show you is here's the first page of the test. Okay. You can have a two-sided formula sheet, formulas only. You could have conversion factor or something like that, but no worked examples. We'll collect these. Just as previously, just like the practice test, there's 3 questions, they're each worth 10 points. Question 1 has 10 parts, 1 point per part. Let me reiterate what I said. Since only worth 1 point, you've got 3 minutes to do them. Don't start spending more than that. You'll run out of time to do these other questions that are worth more points, so don't do that. And you want to give correct units, okay? And I've said what units are acceptable, and make sure your signs are right, okay? Now, there is one thing that I noticed. The book has a different sign convention for bending moment. It tends to make the bending moment compressive on the bottom. The more usual sign convention is compressive on the top. Okay, well, I will tell you what sign convention to use in the test if there's a bending moment question. But it's become popular in academic circles to switch this long time sign convention, but in engineering practice, it hasn't switched. It's still the civil engineering convention where it's like the floorboards you walk on, they get compressed on the top. And so that's what the first page will look like. Okay, at this point, I'll take any questions you have about the test. And this will be your only opportunity to ask questions. Oh, I should point out, there'll be no class next week. We've got Mardi Gras and we don't have a problem set, so there's no problem session. And the test will be returned to you the following Monday after the lecture. Do I have any questions?
I think there's one in the chat.
Sorry?
Somebody asked if there could be any words describing the formulas for the formula sheet.
Oh, yeah. Yes, that's clear. I mean, the idea of the formula sheet is to stop this being a memory test. And so you write down all the stuff you need about the formulas so that you can use them. Now, if you remember how to use them, and you actually, if you even remember the formula, you don't need it. So it may be for some of you that you don't need 2 sides. Don't worry about it. But just go through and look at the problem and say, what do I need to solve this? And I'm telling you, you don't need KT charts. Maybe that's what you need to solve it. You'll be given that. And you don't need material properties. Okay? You don't need that stuff. But what else do you need to solve these problems? And if in doing that, you need to remind yourself that this is the nominal stress or something else, and you want to describe it a bit, that's okay. It's okay. What happens in practice is you work in a certain area, and after a while you learn the formulas, and you hardly ever need this sort of stuff. But you're learning a bunch of stuff in different courses and so on. And so your day-to-day use of them is relatively limited to what's in practice. So having something like a formula sheet is fine. If I'm working in an area and I haven't been in it for a while, the first thing I do is go get my first book and make sure that I'm not making a mistake in some of the formulas. Yeah. Any other questions? Yep.
Yeah. Other than horsepower, are there any other non-traditional units that you would give us that we would need to be able to convert?
Oh, yes. I didn't talk about power in that little list. I did force, length, and stress. But there's nothing really. I mean, horsepower is yes, that's the only one. So if you want one to put units for power, be horsepower, be watts for SI units, Newton meter per second. Excuse me. Anything else?
Are we allowed to put these, like the unit chart you gave us, could we put that on a formula sheet?
Sorry, what's that?
Like the unit chart you gave us, could we put that on our formula sheet?
Oh, yeah.
So this is just more of a content question, but for pressure vessels, when we are given a problem where there's only internal pressure or there's only external pressure, and we have to calculate the max shear stress, when we do that and we're calculating that value, are we just looking at whatever value of theta 3 would give us a max shear stress? So for example, we choose between theta 3 equals 0, or I'm sorry, not theta 3, sigma 3 equals 0, or sigma 3 equals the negative pressure. We just choose which of those values.
And if you do that, you find that the maximum shear stress is the same for both external and internal pressure. Because
okay, thank you.
You know, you get a hoop stress, which is the biggest tensile stress for internal pressure, and you subtract minus P from that. When you do it compressive, you add P to the hoop stress, and it becomes compressive. So that's a bigger compressive stress. But now you don't want to subtract a compressive stress from that. That would knock off the P, so you take 0. So you get the same outer plane shear stress in both cases.
Okay, thank you.
Dr. Sinclair.
Yes, sir.
What did you say the unit for power for US units is?
For US units?
Yeah, what did you want us to use?
Well, what you've had in problems, you've been given some horsepower, and you want to turn horsepower into pounds, force, feet per second, because then you can get stresses, get torques from it or something like that. Okay, and so if you're given horsepower, which is 550 foot-pounds per second, then you need to change it to foot-pounds per second. So I didn't put time, the unit of time for both US and SI units is seconds. Okay, and so foot-pounds per second is the underlying unit that you can use. You divide by omega, which is say the RPM or something like that. That has to be in radians per second. Radians is not a unit; it's just a number. And then you'll get torque in foot-pounds, which is what you need. Now, when you start to work out shear stresses, and you're working T R upon J or 16T upon pi d cubed, then the D is going to be in inches, so T can't be in foot pounds, it has to be in pound inches. So you have to multiply by 12. But you had a homework problem just like that.
Gotcha. Oh, another question.
Yeah.
Do you need us to derive the moment of inertia for some of the stress equations, or will that moment of inertia be given?
No, yeah. Just look at the solutions. There's no derivation. Okay. I mean, you're not going to do that in practice. If you don't remember, you're going to look it up. Okay, somebody else would have done it. Okay.
Gotcha.
Okay.
One last question. I know in all the homework problems we've ignored transverse shear for the most part. Are we able to just assume that we're ignoring transverse shear in the test, or do we have to calculate it and show that it's, so little percentage?
that's a wee bit of a judgment. But and look, this question reflects a little bit that you obviously have limited experience in doing this sort of stress analysis. That's not a criticism. That's a statement of fact. Typically, the shear stress due to the shear force, which occurs in the middle of the beam, is nowhere near as big as the bending stress divided by 2, which is the shear stress on an inclined element at the outer of the beam. Okay. Typically 2 orders of magnitude less. So if you want to calculate it and check that out on the test, that's up to you. But it's going to be a lot less by and large. One of the reasons we didn't spend much time on it. In fact, I'm not sure we spent any time on it. There are some extremely stubby, small beams where they're really not beams, actually. The height of the so-called height of the beam exceeds its length. So it's really acting like a plate or something like that. But if you start using beam theory, there occasionally those stresses can be comparable. The shear stresses in the middle of the quote beam can be comparable because the bending moment can be very close to 0. But in some ways, those are not really beams. Okay, you're using beam theory for something. A beam. How do you define a beam? A beam is something that's long relative to its height, and it's in plane dimensions. Okay. So when you get down to these situations where the height is actually bigger than the length, it's not really beam theory. Okay, so you're using an approximation, a questionable approximation when you do that anyway.
Are you looking at ankle?
So what I'm saying is when you really get beams, that shear in the middle of the beam due to the shear force is typically 2 orders of magnitude less, not worth worrying about, especially if you're asked to get the maximum shear.
Thank you.
Any other questions?
Dr. Sinclair.
Yep.
So what was the final verdict on that? Like, do you want us to solve for the transverse shear or just say that it's negligible because the stress due to other?
I would, let me give you 5. Don't worry about it. Okay.
Don't worry about it?
Yeah. Yeah.
Okay. Thank you.
Maybe, were you told to get this when civil engineering taught you mechanics of materials or something?
No, my tutor just always had me solve for it when we were doing problems. So he told me to ask you.
Is that right? Who's your tutor? Okay. Okay. No. All right. Well, I see some of you are trying to send me your letters. You need to email me those letters at my home email. Okay. Your letters for email me your letters that give you extended time to my home email. Thank you. Okay.
Could I also ask a question?
Yeah.
Okay. My apologies if it's been addressed before, but for this test specifically, will we be expected to show linear interpolations for the stress concentration factor?
Will you be expected to show it?
Linear interpolations?
I sort of answered that question earlier. In a test, you don't have a lot of time, but yeah, you could have to do a linear interpolation. Yes. Okay. So if you have a stress concentration factor in the test, it'll be fairly easy to read off the chart. If it's between something, then yes, it would not be unreasonable to do a linear interpolation. Okay.
Okay, perfect. Thank you.
That'll be fairly quick. What I don't want you having to spend time doing, carefully reading from the chart using a scale what the value is for KT for H upon B equals 3 and H upon B equals 2 or something like that. Okay. So those values you can just kind of roughly get, okay, by looking at the chart. But if you wanted H upon B was 2.5, then you'd have to linear interpolate the average of those two. Okay. Anything else?
Dr. Sinclair, I have a question.
Yep.
You were talking about class next week. Do we have class next week at all? Or
No.
No.
See,
Okay.
the lectures are in the morning, so they're both gone. And the next problem set won't be for the following week, so there's no problem session. So the problem session on Friday, there's no problem session for it to address. So there will be no class next week. And the class that follows this Friday test will be not the next Monday, but the Monday following. At that point, we should have the test graded and be able to return them to you, which I'll do at the end of class, hopefully.
Thank you.
Anything else?
Could you go over why we weren't able to use the formula you provided for KT on the elliptical cutout problem that you went over?
Could I go over?
You had given us a problem. You had given us a formula for KT to estimate it when it's an ellipse. But you did a different method for the problem that you gave us on problem set 3.
Okay. What I think I did that. Why don't you look over your notes? If you've got a question about that, ask me in office hours. Okay. Okay. But you might talk to some colleagues. But I pretty much explained what I did. On the other hand, I will tell you that's a slightly tricky question doing that sort of estimate. But you can, with a bit of experience, you can get kind of the right order of magnitude for these stress concentration factors using values. One of the reasons why I say you should get to within 5% of the answer with finite element is because you can probably get within 20% with a bit of experience estimating it from past KTs. But when you do that, you're always a little bit uncomfortable, unsure maybe, just how good your result is. And so something like that, in practice, I would do it as a first estimate, just to see roughly what the stresses are. And so that KT I got was 18. And if you multiplied it by the applied stress, and the applied stress turned out to be 2 KSI, and it's a piece of steel, then it doesn't matter. You don't have to bother doing it more accurately. Even if the KT turned out to be 36, it's still only 4 KSI, and steel has much higher yield strength than that. Okay, doke. All right, well, we'll see you Friday. Good luck. Okay. Well, I hit end meeting, and what I hit end meeting.
Yeah, end
End meeting for all.
Oh.